Okay, let's talk about Stokes theorem. So today we'll make a connection between the familiar subject, Green's theorem, and a new one, Stokes theorem. So we will realize that this new fangled piece of calc3 is nothing but a generalization of our familiar Green's theorem. Okay, so do you remember Green's theorem on a plane? What does it say? Let's recall Green's theorem. Okay. It just relates an integral, double integral over the region in xy plane of some combination of partial derivatives of your vector field dq, namely dq dx minus dp dy, dA with the line integral over the boundary over the region. So the curve, which is the boundary of the region of p dx plus q dy of the work done by your vector field. Good. And last time we also, or maybe the time before, we interpreted it in a vector form, and actually two different ways. But today we'll need the interpretation which relates the line integral understood as the work, that is FDR. Or maybe if you want to be more specific, you will recall that dr we can rewrite as TDS as the magnitude of r prime ds, and eventually we will end up with this expression, integral of the tangential component of your vector field along the curve with respect to arc length, tangential component of f. On one side, and on the other side, we will have the curl of f dot product with k, which now we attempted to think about as the unit normal vector to our surface, the flat region D in the xy plane. Of course, the normal is just k. Okay. So in fact, if we now get out of the plane, so if this was the region D in the plane, xy plane, and if we get out in 3D, so instead of region D in the plane, we think of a surface in 3D whose shadow is this region D. So it drops a shadow, but we are looking at the surface, 3D surface. Then the Stokes theorem will tell us that if we do the double integral over the surface S of the curl f ds. So by this dot product, just like with this dot product, we have to interpret it somehow. So that we interpret it as f r prime dt. Then this, remember our interpretation from last time was we have to do the dot product with the unit normal to the surface, and that's guaranteed to exist if we're talking about orientable surfaces. ds, so where this is now scalar, area element. So Stokes theorem will tell us that this double integral over the surface or surface integral should be exactly the same as if you calculated the work over the edge, over the boundary of this surface, FDR. Okay, so let's try to understand a few things, starting with the relationship between the surface orientation and the orientation of this curve C, the boundary of the surface. The claim is that the surface, if oriented, and the orientation is essential here, it guarantees us the existence of a continuously varying unit normal. So orientation is key to write in this integral, the double integral, the surface integral. So surface is oriented. It comes with orientation, so that we would be able to write this integral. It turns out that this orientation gives us the orientation on the edge, or mathematicians say the orientation on the boundary of the surface is induced from the surface itself. How? That's a good question. So let's take a look at the nice picture here. What are we seeing? In this case, we're assuming that our surface is oriented upwards. Doesn't really matter. If we have the upwards, in this case, orientation, then we can think of this small little guy walking erect around the boundary of the surface. So it may be working around on the surface as well. But then when he comes out to the edge, then he has several ways to walk around. He can walk around in this direction, or he can walk around in that direction. So if we agree that as the person who walks on the surface is walking around so that the actual surface is observed on through his left shoulder, or hers, then this will naturally induce the orientation on the boundary. So it will tell us, okay, if we have to see the surface on our left, then there's only one way to walk along the surface. So it means that we have to walk in this direction. So if we are finding ourselves here and we have to see the surface on our left as we are walking, then we have to follow this direction. And that gives us the orientation on the boundary of the curve. Good. So then we can talk about the line integral. That's what happened here. Okay. And even though it doesn't give us a particular parameterization on the boundary, it tells us that the orientation, the parameterization we choose to calculate the boundary integral has to be of certain orientation, has to be compatible with orientation on the surface, or has to be induced with orientation on the surface. So under these two conditions, that orientation of the curve and the surface are compatible in that way, we have the Stokes theorem, which tells that to find the work around the edge of your surface is the same as to find the integral of the curl as projected onto the unit normal to the surface over the surface. Same as the double integral of the curl over the surface, roughly speaking. But if you look in detail, it's not, the curl is a vector, we have to create a scalar function. So the scalar function here is curl f dot n. And that is integrated with respect to s. So again, if your surface is given by parameter u and v, then you would keep on writing, you would keep on setting this up as curl f dot n, and then the magnitude of RU cross RV dA over the domain, could be the domain in the XY plane, and UV could be X and Y, or more complicated situations. But that is the Stokes theorem in a nutshell. Now let's understand it. How does it come out? How does it grow out of the Green's theorem? In fact, you can see the book proves a specific simple case of a Stokes theorem using exactly that, using Green's theorem. So try to follow this proof. It's maybe 10 minutes of calculations, but very didactic to see once. So let us see the connection with the Green's theorem. So let's assume that we are looking at a particular surface, which is flat, and which is just lying in the XY plane, like this. So if we try to apply Stokes theorem to this flat region, to this flat surface, then all we are seeing is curl f dot n dA, or I should say ds, over d has to be the same as the usual FDR over the boundary. Well, that is, of course, just f tangential component dot t ds with respect to arc length over the boundary C. But the left-hand side, what is the normal? What is the unit normal to the flat surface like that? That is just k. Well, we realize that that is just the vector form of the Green's theorem, which we studied before. Because ds is exactly dA, that is dx dy in this case. So we see that we can conclude that Green's theorem is a special case of Stokes. Think about it, but let's move on to an example. So Green's is a particular case of Stokes. And in fact, if you walk through the steps in the proof, you will see how it is proved again by reducing it to the Green's theorem on the plane. Okay, let's take a look at this example. We have to evaluate the line integral over a closed curve. Which closed curve? The curve of intersection of the plane and the cylinder. Plane y plus z is equal to 2. Good. So let's find some space. Well, maybe let's take a look at the picture. So that's a very nice picture. If we intersect the z plus y equals 2 plane with the cylinder. then we will see this surface bounded by what looks like an ellipse. And we have to integrate, we have to find the integral over this ellipse of this vector field. So in other words, we want to find the work of this vector field over this ellipse. It's not a big deal to parameterize this ellipse and find it directly. But why don't we use the Stokes theorem to calculate the work here? So the work, which is FdR, can be found using the Stokes theorem. That is, we can come up with a surface of which this curve is a boundary. And we have to mind, of course, the orientation. So there are many surfaces which will be bounded by this curve, but the simplest one is, of course, this bluish flat piece of plane of y plus z equals 2 plane bounded by this ellipse. So that's what we'll take as our surface, and according to Stokes, we can say that that should be same as the curl f dot n, the unit normal to the surface, and we will take, of course, upward unit normal, because that would give us the correct orientation on the boundary, ds. Okay, so what's the first thing that we have to do? Well, we have several things, one of which is parameterizing the plane. Well, this piece of surface, but that is clear how to do. The parameterization is in terms of x and y, since it's the surface easily described as z equals 2 minus y. So parameterization is x, any x, y, and then 2 minus y for z. So that is the parameterization for the surface. And then the next order is what about the curl? So, well, curl f we'll have to find out by usual methods, ijk. Then we'll plug in the partials, dx, dy, dz. And the third row would be minus y squared, x and z squared are the components of a vector field. So we will have for the first component of the curl, partial y of z squared is nothing, minus partial z of x is also nothing, 0. Second component is partial x of z squared is nothing, minus partial z of y squared is negative y squared is also nothing. And finally, the third component, k dx of partial x of x is 1, minus partial y of negative y squared is negative 2y. And we'll end up with 1 plus 2y, k. Good. So that is our curl. And then we can compute, maybe let's compute separately n. How do we understand n? So since that is the surface parameterized using x and y, then by unit normal, let's take the, so normal to the surface would be Rx cross Ry would be what? Do you remember the formula? Minus Zx minus Zy and 1. And then we have to divide by the normalized by the magnitude of this vector. So let's calculate. Minus zx, partial x is 0, partial y is, z with respect to y is -1. So we have minus minus 1. And finally 1. And that has to be divided by the magnitude. So the magnitude is square root of 1 squared plus 1 squared, or square root of 2. So we have 0, 1, 1, square root of 2. So the shortcut, maybe even if you don't want to calculate n, we can even write it as, let's continue here, as the double integral of curl f we can remember that ds, or just instead of n, we can just use ds, which is just ru cross rv, or rx cross ry. dA times dA, which by that we mean dx dy. So we can write here as, we can just use curl f 0, 0, 1 plus 2y dot with rx cross ry, which is minus x minus zy and 1. So we already noticed that that is calculated right here. Rx cross ry, 0, 1, and 1. So we don't need to worry about square root of 2 here. dA. Now what is the xy region? So since now we are in terms of doing everything in terms of xy coordinates, then we're looking for the region in the xy plane. That's of course whatever is outlined by the cylinder. And what kind of cylinder is that? That's the unit cylinder. X squared plus y squared equals 1. So over this region D, which is the unit circle or unit disk. So let's calculate the interior dot product. That of course will be just 1 plus 2y. And over the unit disk, it's advantageous to take it in polar coordinates. In other words, so in polar, we'll have that we're integrating y would be written as r sine theta, and instead of d we have r dr d theta, r measuring from 0 until 1 for the unit disk, and theta from 0 until 2 pi. So if we distribute this r, then we'll have to integrate r plus 2r squared sine theta with respect to r from 0 until 1, and then with respect to theta from 0 until 2. So we'll get r squared over 2 plus 2r cubed over 3 sine theta from 0 until 1, and then with respect to theta from 0 until 2 pi. You can see that you get here 1/2 plus 2/3 sine theta. What can we say about sine theta? Okay, let's do things slowly. So we'll get 1/2 times 2 pi. Here we'll get 2/3 times negative cosine theta from 0 until 2 pi, but we know it's periodic. So at 0 and at 2 pi, it will have the same value, so it will cancel. So and we'll get that the overall result is pi. And that ends this example and today's video. See you in class.